Hello, listeners. This is Mike, your host. If you are enjoying these archive episodes, please consider supporting the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange donate button or the Patreon link. Hopefully, with your support, I can continue to release these archive episodes. Thanks.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
My feel out. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Listen, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 146 of the Space Rocket History Podcast. And now, Saturn S2 stage. The Saturn S2 was the second stage of the Saturn V rocket. It had 5 J2 engines in a quincunx pattern. The center engine was fixed, while the other 4 were gimbaled. They were fueled by liquid hydrogen in the top tank and liquid oxygen in the bottom tank. The second stage was capable of accelerating the Saturn V through the upper atmosphere with 1 million pounds or 4,400 kilonewtons of thrust. North American won the contract for the Saturn S2 stage. NASA officially announced the company's selection on September 11, 1961. After consultation and search for a manufacturing site, a location at Seal Beach, California was chosen, and facilities for constructing the S2 were built by the government. The S2 turned out to be a challenging stage in terms of the existing state-of-the-art. Although the S2 carried about 426,400 kilograms of liquid oxygen and liquid hydrogen, the tank structure accounted for just a shade over 3% of the stage's total fuel weight. A common bulkhead, much larger than any other previous rocket, averted the need for an interstage between the oxidizer and the fuel tank. And what I mean by a common bulkhead is the hydrogen and oxygen tanks shared one of their end caps. The common bulkhead was located at the bottom of the hydrogen tank and the top of the oxygen tank. The common bulkhead had the advantage of reducing the total length of the stage by over 3 meters and saved about 4 metric tons of extra weight. But the use of the common bulkhead also created one of the major problems encountered during the construction of the S2. In technical terms, the fabrication of the bulkheads called for unusually demanding accuracy in the meridian welds that join the bulkhead triangular metal sheets called Gores together. The welding operation, joining the curved 6-meter-long seams together, had to be made to specifications allowing less than 1/3 of a millimeter of a mismatch. The common bulkhead, with its 10-meter diameter and 6.7-meter height, had a squat appearance with no vertical walls to speak of. The liquid oxygen tank was constructed by welding dozens of Gores together and finishing off the tank with large circular pieces joining the ends of the Gores at the top and bottom. The top of the LOX tank actually formed 1/2 of the common bulkhead. After welding this part of the LOX tank, the common bulkhead was completed before adding the tank's bottom half to it. But this was much easier said than done. Early on, the forming of the Gore segments for all the bulkhead assemblies frustrated manufacturing engineers, because no technique existed for forming such large, unwieldy pieces. Each gore was approximately 2.6 meters wide at the base and had complex curvatures that were difficult to form accurately. After rejecting numerous possible procedures, the manufacturing team finally chose a somewhat exotic underwater explosive forming. This technique quite literally blasted the wedge-shaped gores into shape. North American's Los Angeles division produced the gores using a 211,000-liter tank of water at nearby El Toro Marine Base for explosive or high-energy forming. After positioning the gore segment in the tank, engineers detonated a carefully located network of primacord explosive, forming the metal by the blast transmitted through the water. The formation of each gore required 3 separate blasts. Beginning with the upper half of the LOX tank, fabrication of the common bulkhead required a number of carefully timed and sequenced operations. First, honeycomb phenolic insulation was fitted over the upper surface of the liquid oxygen tank dome, called the aft facing sheet because it served as the bottom of the common bulkhead. Then the insulation was bonded to the aft facing sheet and cured in a gargantuan autoclave. Next came the preliminary fitting of the forward-facing sheet. This piece became the bottom half of the liquid hydrogen tank, which was also formed from large wedge-shaped gores. Preliminary fitting of the forward-facing sheets revealed surfaces in the insulation that needed to be filled in or shaved down for a perfect fit. Using a machine controlled by data tapes, throughout the process, numerous checks were made to ensure that no gaps were left between the insulation and the facing sheets. Ultrasonic equipment verified the complete bonding of the adhesives. Fitting the honeycomb core to the bulkhead domes was one of the most critical operations in the S2 manufacturing sequence. The chemically milled gores tapered from about 13 millimeters thickness at the base to 0.79 millimeters at the apex. With these thin sections, the great domes possessed relatively little strength by themselves and tended to sag. This situation created several production problems in achieving the close fit required between the top and bottom domes and the insulation core. The honeycomb sandwich, which comprised the gore, measured nearly 13 centimeters thick at the peak of the common bulkhead and tapered off at the bottom periphery, where more thickness was not necessary. So the honeycomb core, like the gores, had to be shaped to complex curvatures, tapered, and affixed without gaps to the flexible dome surfaces. The procedure finally worked out by North American manufacturing teams was heralded by the company as a major advance in missile fabrication. Workers applied a low-pressure inflation force to the aft-facing sheet, giving it full contour and providing accurate dimensional traces for fitting the honeycomb insulation core. The forward-facing sheet presented a different problem. Since the top surface of the insulation core had to be fitted to the underside of the forward-facing sheet, the inflation technique was ruled out. Instead, North American devised a huge vacuum bell fitted over the forward-facing sheet. The vacuum bell sucked up the sheet to a fully contorted position. Afterward, handling slings lowered the entire assembly over the rigidly pressurized aft-facing sheet to record the final set of dimensional traces for shaping the insulation surfaces. At the bottom edge of the forward-facing sheet, a J-shaped periphery provided the surface for welding it to the bottom cylinder wall of the liquid hydrogen tank. These J-section segments had to be separately machined and form-fitted. A circular weld at the J-section joining the LOX and liquid hydrogen tanks was buttressed by a bolting ring. 636 high-strength bolts secured the bolting ring to the flanges on the bottom of the liquid hydrogen tank cylinder and to the aft skirt section. The bottom cylinder measured only 69 centimeters high. The remaining 5 cylinder walls, each 2.4 meters high, were fabricated in 4 sections and welded together. The curved aluminum skins were machine milled to leave stringers and ring frames for both structural rigidity and for mounting the internal slosh baffles. The liquid hydrogen forward bulkhead was fabricated of 12 gores in much the same way as the LOX tank lower bulkhead. Another challenge was the problem of insulating the big liquid hydrogen tank filled with thousands of liters of the supercold propellant. The insulation tank created some of the most persistent technical problems in the entire S2 program. North American chose external insulation primarily for added material strength from the cryogenic effects of liquid hydrogen inside the fuel tank. This trade-off confronted the company with the problem of adequate external insulation and with special difficulties in bonding the insulation to the supercold surfaces of the fuel tank. The original solution specified external insulation made of phenolic honeycomb filled with a heat-resistant foam of isocyanate. Fabricated in panels, the insulation material was sealed at the top and bottom with a phenolic laminate followed by layers of Tedlar plastic film. The process of bonding the insulation panels to the tank created potential hazards. Air pockets next to the super cold metal could be turned into puddles of liquid oxygen. These puddles could eventually weaken the bonding, thereby allowing large panels to peel off. To avoid this, the S2 stage featured a liquid helium purge of the insulation through grooves cut into the insulation surface next to the tank walls. Helium flowed through the grooves from the start of hydrogen loading through the countdown and up to the instant of launch. Unfortunately, this design never worked very well. The purge system was tricky. The insulation bonding repeatedly failed, and chunks of insulation continued to fall off during tanking and test sequences. Although several S2 stages were produced with the original insulation concept, the results were so discouraging that North American spent considerable time and money working up an alternative. Instead of making up panels and affixing them to the tank, the company finally evolved a process for spraying insulation material directly onto the walls, eliminating the air pockets, letting it cure, then cutting it to the proper contour. This technique turned out to be much more economical and much lighter than the insulation panels. Moving on. Then there was the welding problem. The size of the S2 included dimensions normally associated with bulky fittings and burly strength of heavy industry. The inside of the S2 was roomy enough to stack 3 standard railroad tank cars end to end, with room to spare for a caboose lying sideways on the top. Yet the 24.8 meter stage weighed only 43,100 kilograms in its dry state, as compared to 3 empty tank cars, which weighed more than 95,700 kilograms. In spite of its massive appearance, the S-2 was honed to the precise standards of the watchmaker. Almost 1 kilometer of welded joints had to be surgically clean and flawless, and many had to be accurate to 1/3 of a millimeter. The structural efficiency of the stage in terms of weight and pressure taken by its extra thin walls was comparable only to the capacity of one of nature's most refined examples of structural efficiency, the egg. One problem was the nature of the tank's skins themselves. The S-2 was built of an aluminum alloy known as 2014 T6, which was not generally favored for welding. North America knew the welding job was going to be complicated, but wanted to use the alloy because of its enhanced strength under cryogenic conditions. A theme of the entire Saturn program was size, and the challenges inherent in the S-2 were similarly challenges of magnitude. With a diameter of 10 meters, the stage required circumferential welds of 31.4 meters. The longer the weld, the tougher the problem of sustaining quality and close tolerances, and in the S-2, weld quality and close tolerances were essential. A high-quality weld pass of 1 meter might be one thing, but a virtually flawless circumferential weld of 31.4 meters promised all manner of increasing heat input problems and attendant distortion problems where none could be tolerated. The various aluminum sheets joined together in the welding process varied in shape, size, and thickness, all of which caused different problems for the welder. One such joint had skins that tapered from 16 millimeters thick down to under 6 millimeters, then back up to 13 millimeters. Weld speeds, arc voltages, and other regimes had to be tailored for each variance during the welding pass. Minuscule cracks, tiny bits of foreign material in the weld seams, moisture, or other apparently innocuous imperfections could leak volatile propellants or cause catastrophic weakness under the pressures and load experienced in flight. The tank cylinder walls posed a far different set of problems. Each wall was machine formed and assembled by many different manufacturing methods. Each varied because of the stresses of movement from one industrial site to another and exposure to different influences of heat and climate. This was one of the most difficult aspects originated in the initial fabrication process. Each of the 4 cylinder sections was machined as a flat piece, then contour shaped and welded together, with different stress factors from one complete cylinder to another. Before each welding operation, technicians reminded themselves that the cylinders were seldom true circles with nice flat surfaces for welding. During one of the first attempts to weld 2 cylinders together, 80% of the job was complete when the remaining sections suddenly ballooned out of shape as a result of heat buildup and increasing stress from distortion. Exasperated specialists brainstormed the aggravating phenomena and tried to come up with a suitable fix for the problem. As a result, all the welded parameters had to be revised to include different tooling and new procedures using a series of tack welds evenly spaced around the circumference, followed by 3 more passes using 2 skate welders operating simultaneously 180 degrees apart. One of the most trying welding jobs in the whole operation was the joining of the forward liquid hydrogen bulkhead to the uppermost liquid hydrogen tank cylinder, where the mismatch could be no more than 0.69 millimeters. Time after time, weld defects or mismatches occurred. Each reject required time-consuming efforts to cut open the weld, realign the pieces, and start over again. Delays at this step began to disrupt the whole program and raised the specter of late deliveries and slips in the launch schedule. To alleviate some of the problems, the existing humidity conditions in the manufacturing area were reduced from 50% to only 30% to enhance the probability of a better weld quality. An environmental control room, clean room atmosphere was established by hanging huge canvas curtains in one corner of the assembly building. Personnel had to pass through a double-door airlock to get in and out of the welding area. They were required to wear white, lint-free smocks and gloves, as well as step through an electric shoe brush machine to remove dirt picked up from the floor outside. Inside the clean room, workers continually mopped the epoxy floors to keep them free of moisture and extraneous particles. No smoking or eating was permitted in the area, and adjacent walls were painted a stark white to remind everyone in the vicinity to think clean. With manufacturing specifications of these magnitudes, North American experienced many long months of frustration until processes were completely under control. Not until January 1968 did North American succeed in performing an error-free weld for the bulkhead to cylinder joint. This feat was accomplished in the build of S2 number 9. By that time, there were only half a dozen stages left to produce. The previous stages had gone out of the factory door with histories of shortcomings and corporate frustrations of considerable scope. The technical complexities of the S2 help explain the rash of problems encountered during its manufacture and test, and serve to highlight the trauma of North American aviation under fire from NASA and from Marshall Space Flight Center. Now a word about the systems of the S2. Of the 6 major systems, the propellant system was the most complex. The 7 propellant subsystems included plumbing, hardware, and control to accomplish the following: purge, fill and replenish, venting, pressurization, propellant feed, recirculation, and propellant management. Elements were largely designed to cope with the tricky characteristics of the cryogenics carried on board the S2 stage. By using helium gas, the purge subsystem cleared the tank of contaminants like moisture, which could freeze and block the valves or vents in the LOX tank, and oxygen, which could freeze and create dangers of explosions in the liquid hydrogen tank. The fill and replenish subsystem, along with the recirculate cycle, helped relieve the tank's valves, pumps, and feed lines of the thermal shock encountered from the sudden introduction of ultra-cold propellant into the stage. The recirculation subsystem kept propellants moving through the engine pumps and associated plumbing while keeping them properly chilled and ready for operation. Similarly, the fill and replenish system brought the propellant tanks and their related plumbing down to a temperature suitable for loading the cryogenic propellants. Other major systems, including electrical, ordnance, measurement, thermal control, and flight control, were similar in basic function to those on other Saturn stages. The same was true for the ground support operations for checkout, leak detection, engine compartment conditioning, and other equipment. With the parts and pieces accounted for, we will move on to the assembly. Eventually, all the parts of the S2 came together in the Vertical Assembly Building at Seal Beach, California. Vertical assembly was chosen for its advantages in joining major parts and ease of welding. In vertical assembly, as opposed to horizontal assembly, it was much easier to maintain circumference of the large diameter parts to close tolerances, and gravitational force helped maintain stage alignment. Moreover, if the various cylinders and bulkheads were horizontal, temperature diversion about the circumference of parts would produce distortions at the top of the piece being welded. Throughout each welding sequence, technicians employed a variety of special scopes, levels, and traditional plumb bobs to make sure alignments were exact. Additionally, the stage was subjected to hydrostatic, X-ray, dye penetrant, and other checks to ensure proper specifications. One of the last items to be added was the systems tunnel. Affixed to the exterior of the stage, the tunnel, a semicircular structure, ran vertically up the side of the S2 and carried miscellaneous instrumentation along with wires and tubes that connected system components at the top and bottom of the stage. Final work inside the tanks included installation of slosh baffles, probes, and other miscellaneous equipment. In preparation for these operations, all surfaces inside the tanks were thoroughly cleansed, flushed with trichloroethylene, and dried. Flushing equipment consisted of a spray nozzle fitted to a movable lifting cylinder similar to the hydraulic lifts used in auto repair shops. After the flushing, a team of technicians mounted a ladder and platform attachment on the movable lifting cylinder, entered the tanks, and began final installation of equipment. With all accessories installed, the tanks had to be flushed once again and the access ports sealed. Finally, the engines were mounted, again using accurate alignment equipment to position each J2 in the thrust frame attachment points. Additional stage test and systems checks preceded final preparation for shipping to the Mississippi test facility for the static firing checks. After testing at Mississippi, the stage would be delivered to Cape Kennedy for launch. Now let's spend a little time on how the S2 operated. After launch, in a sequence known as dual plane separation, the interstage, although joined to the aft skirt, uncoupled from the S2 after staging from the S1. Following burnout of the first stage, a linear-shaped charge separated the S2 from the S1. This procedure was simultaneous with the firing of the S1's retro rockets and 8 ullage motors in the inner stage of the S2. About 30 seconds after first stage separation, the S2 inner stage separated from the second stage itself. Initiation of the dual plane separation maneuver occurred when the outboard J2 engines reached 90% of their maximum thrust. At this point, explosive charges were triggered, which severed the interstage. The maneuver required a precise separation that would propel the interstage rearward, clearing the engines by approximately 1 meter, while the S2 was accelerating to its top speed. Once free of the interstage mass, the performance of the S2 was greatly enhanced. The dual plane separation was an alternative to a method called fire in the hole, which involved ignition and separation of the S2 while still in contact with the interstage but not attached to it. Designers preferred to avoid this alternative because of possible perturbations and oscillations at the end of the first stage boost phase. With the S2 accelerating on an even course, it was easier to drop the interstage during that phase rather than risk hitting a wobbling interstage attached to the S1 as the S2 pulled out. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.